as you want.
Hello. Yeah. So let's get started. So this is the last one in this summer school. I will talk how do we call AI in Gadgetron. So can you see my slides? Okay, so this is newer stuff. Let's see how we can use Gadgetron to call AI, then building something new for the clinical imaging. This is outline for this course. So we will start by motivate why we want to do this. Also, we will touch the concepts of inline versus offline. Then we look into Gadgetron Inline AI, which is a package or scheme Gadgetron provides, so we can call the AI models. Then I prepared two examples for this course. One is rather demo, running Grappa as an AI model. It's served as extension of generic chain we mentioned. And as an example, if we want to do the AI-based reconstruction, Gadgetron can serve as a purpose. The second example is more mainstream use case that we can extend it to the imaging pipeline for the image analysis. For all the demos, we will walk through some code, and I also upload the data and the instruction to the course website, so we should be able to reproduce this. Then finally, I have final remarks for this course. So let's get started. With deep learning coming into the mainstream, definitely these days, one key task, if we want to use it for the MR imaging, is to be able to do model inference on the scanner. When I say on the scanner, I mean a rather broad concept, not literally on the scanner, but functionally. So we have to have the trained neural net models. Then they often require lots of computing power to compute, and also needs more latest. It's more serious that it needs more latest software configuration to call these models. But on the scanner side, if you check vendor-provided environment, especially those old scanners, so every year the scanner replacement is about 5–10%, which means the old device will be up there for at least a decade or longer. For those devices, they have limited computing power and more seriously, the software version is so updated, we just can't run the newer AI software framework there. And also make this whole thing useful, the model inference has to be done at the clinical relevant time. It cannot be too long. So it's still not so easy to deploy neural net models to the imaging work pipeline. This comes to what Gadgetron can offer. So if we look at the common way of, let's put it this way, established way of how operator using the scanner or maybe running the AI models, it's more like interactive processing. Some vendor will provide a software sitting on an external server. Then image was exported into this server. Operator often needs to log into this software, loading the image, then either run the model or correct the answers. This process is not only tedious, but the key point is it will use lots of expert time. actually, for many of our users, they spending hours literally every day on loading the image, viewing them, find the series they should run a process. You know, all this non non-essential tasks take lots of expert time. So what Gadgetron is good at is to offer an inline way of computing, which this possibility is enabled by the deep learning in the sense that previously they are inline processing already around for years. But what it can do is rather limited because in the previous time, we can't even reliably detect, let's say, a heart in the image. As a computer vision task, it's very hard to make it work clinically. But with at this time, with the neural net models, all these tasks become solvable. So it's open lots of opportunities. So I can give you a few examples what we did with Gadgetron. For example, this one, we can do inline Cine analysis. If you do a Cine scan, Gadgetron will reconstructed the image, then take the image, apply the AI models, then give you the this kind of report for the common metrics used by cardiologists. You can see this segmentation endo-IP contours. For every slice, it's give you the mass, how many gram, and also all these parameters. So we have to ask how many percentage, what's the acceptance rate, which means for every 100 consecutive patients, how many times clinician can decided to use the number of this application spit out. With the deep learning, it's this whole problem is solvable. So we can achieve at this moment like 85% of the case. So that's one example. There are many other examples we had investigate. For example, doing the perfusion reporting, also doing denoising using the Gadgetron inline applied to the image. So on the right, this movie actually showing how this looks like. You can do a normal scan. For example, the real-time Cine scan, which I showed in the previous talk. This could be linked to the AI framework. Then you can extracted contours, everything show up nicely on the scanner, even the report. So in the Gadgetron, what do we really offer? So Gadgetron offer two schemes which we can use to call the AI model. One is the Python Gadget. So suppose the model is your model and the inference code is in Python. I will talk C++ later. So one way is Python Gadget, which Christopher Oliver has showed before. You can write everything you do as a Python Gadget, then receive the image, load the model, apply to it. Another interface I found often easier for integration is in the C++ to call Python. So we have this Python function utilities. Then it can calling into the function defined in a Python module, which what I mean is Python script. For example, often to be load model and apply model. I will give specific example of this. Then in this way, you can do the model inference in the Gadgetron chain. The key point is we can utilize the existing Gadgetron chain, then extend its ability to calling AI instead of build everything from scratch. That's actually important because we want to augment the ability of MR imaging, not to replace it. This is some other ways. So with last year or maybe past 2 years, the Pytorch and the TensorFlow, they both increased their support for the C++, native C++. I have to say a lot. So it's now possible we have pre-trained model, then writing everything into C++. So in this way, we can link Gadgetron, for example, to libtorch, which is Pytorch C++ library, then calling the model. This ability is coming over, I think, after Pytorch 1.4. Besides the ability to calling models, what Gadgetron support is a rich format of data, because data is a key component here. As we already learned in this course, we can do case-based data imaging, all kinds of waveforms. We can have metadata as XML format. We can have counters, landmarks. Because all these software modules is open source and they can be changed. So if we have newer data formats, for example, there has been lots of discussion to extend waveform. They all can be combined into this data format Gadgetron supports. Then it can be finally fed into the AI. So one thing we were investigating is using ECG and image for some disease detection. So all this can be done in the Gadgetron framework. So we only need to be, it's like imagination, not limited. So I will come to some examples. Let's look at one example. Let's using Pytorch to run some Grappa recon. So recall Grappa recon. How do we do a Grappa recon? Let's say we have acquired a case-based line as this solid line. Then we have mating lines as this dotted line. So we want to estimate Grappa kernel by all these red points to this green point, to this blue points. That's one set of Grappa kernel. By assemble and solve the matrix like AX equals B. So calibration data A is from reference data. Then B is this missed data from the calibration. Then we can solve the kernel X as a linear equation problem. So these figures actually give Grappa coefficients, how it looks like if you plot them. So in Gadgetron, we default using the 2D kernel, which means, for example, in this case, 5 by 4, so 5 points along the readout and 4 along the first encoding dimension. When we do the reconstructions, it's actually just involve another matrix multiplication. So we extract every 5 by 4 by channel patch from the imaging data. Then we apply the kernel to estimate the dotted line. Then we just fill that dotted line back into your case space. Then you got the full case space. This is a rather elegant and simple approach. But as a demo, I want to call the Pytorch for this application. So step 1 I need to do is to, firstly, I don't want to re-implement the Grappa utilities in Python again, because we already have them in C++, well tested, has been there for a long time. So step 1 Gadgetron can let us to do is wrap the existing C++ function in Python modules, for example, showing here. MRI call Grappa Python. It's using the boost Python for the wrapping. So you can have a wrapper class, which I defined Grappa 2D, including calibration, compute kernel matrix, and reconstruction. Then it can be wrapped as a Python module, and Python can call this. Then we want to apply the kernels to the incoming case-based data. So it was done in this Grappa-AI py file. This is using a Pytorch. So the current framework like Pytorch, it doesn't support the complex data format, but we can still do this as a real imaginary separate. So this computing plot actually showing if we want to separate the real and imaginary to a matrix multiplication, what we should do. So we can have two linear layers in the Pytorch. What linear layer in Pytorch do, or in all the deep learning framework is doing a basically matrix multiplication plus a bias, AX plus B. So we can declare linear layer with bias be off, which means that we will not have a bias term, and it will be just doing matrix multiplication. Then we can set this kernel, its coefficients by the Grappa kernel. We estimate this Grappa layer. Then if we do the forward step, we can separate to do real and imaginary and sum the results. So like this torch final step, torch cat, to get complex outputs. So that's one way to using Pytorch utilities to do a Grappa reconstruction. It's certainly a toy model, but you can consider it. If you want to do a GPU-based recon, then if you can fit the algorithm into existing deep learning network, then you get the GPU recon for free because all this operation has GPU versions. Then I put together another generic chain XML. It's called generic Cartesian Grappa AI XML. It's almost identical to the generic Cartesian Grappa XML. So only thing changed is a new gadget is implemented. It's called Grappa AI gadget. What it's doing is it's derived from Grappa gadget, but it will using this Pytorch version of implementation for the Grappa reconstruction. So I will switch to the other computer. We can look at this code. Okay, so if we look at this Grappa AI gadget, it's not much different than the Grappa gadget. Follow all the conventions of Gadgetron. Has kernel models. So note I have models as this Python object because every model is that Pytorch module which containing the kernels. Then the key function is calibration and perform unwrapping, which is doing the reconstruction. So if I go to this code, firstly, we need to find the Gadgetron path. So by default, when I install the Python scripts, it was installed to share Gadgetron Python folder. So we have to firstly adding that path into the Python interpreter, so Python can find that scripts. That's important. Then, if we go to the key is this type of call. So we're calling Python functions saying, I want to call this create a Grappa AI model function in this Python scripts. So if we go to this Grappa AI Python scripts, which one moment. Where is it? Okay, here we are. So if we look at this Python script, it's like any other Python script. You first import a bunch of stuff. Here it's import the Pytorch, had some utility functions. Then it's defined all these modules. What we calling is this function in this Python script. It's receive a calibrated Grappa kernel. Then what this function do is separate real and imaginary. Then declare the Pytorch modules, then return the module. So in this particular case, we don't have an iterative training step. So it's like assignment is the training because it's not an iterative process. But after we declare this function calling this Python scripts, we can call them in the C++ like normal function, give a kernel that's HOND array, then it will return the models. So normally you can buffer the model as a Python object. It often needs to increase its reference counter so it won't be deleted. Then in the perform unwrapping catch, what it's doing is it will declare another function calling apply the model. If we look at this apply model function, it's taking into your data array and the models which we previously decide, and you can give a device whether you want to run GPU or CPU. Then what this one do is you set the model in evaluation mode, then no gradient because it's a forward path. We don't want to backprop. Then you can call this, it's calling the forward path of this model. Basically apply the kernel on the incoming key space. Then it gives you the recount, put them back to CPU, convert to NumPy array, all these steps. Because we separate real and imaginary, we change it back to complex, then sending back to the reconstruction. So that's a simple example how we you can call in Pytorch for the inside Gadgetron. So we can run these models, run these examples. So I have a small data set prepared. Sorry. This is just R3 phantom data. So I can run it twice. Firstly with generic Grappa recon. So I will delete all my results here. Then secondly, I will run this Grappa AI chain. So I prepared this command here. It's your first time running generic Cartesian Grappa chain. Secondly, we will run the generic Cartesian Grappa AI chain. So ideally, we should get identical image. So I'm running this through this Linux box sitting here. So it's pretty quick, only a single image. We receive one image. Then let's run the Grappa AI reconstruction. So if we look at Grappa AI logs, you can see it's literally calling into the Python scripts. It's initial the Pytorch modules, then perform the reconstruction. So if we look at this C++ recon, we got an image like so. And if we look at the Pytorch recon, got image like so. So worked. We got same type of image. Okay, so that's first examples with showing how we can in extended generic chain to do a AI-based recon. Even this example is pretty in its demo nature, but could be helped to show that how we put all these pieces together. Let's continue to a more real scale example. So one project we did recently is to detect landmarks from this city image for the further analysis. So I'm showing some pictures for the 2-chamber view, 3-chamber view, and 4-chamber view of the city image. So my goal is to detect these 1, 2, 3 landmarks. So my solution is we implement a rather, full-scale neural net. It's based on the residual rise U-net structure. What's input is a single picture. Give you output is the landmarks, which detected using the so-called heat map, which is a rather popular scheme in the computer vision for people to detect the human pose or the, let's say, position of your arm or something. This model was trained on a full-scale data sets, like 11,000 more pictures. It has 25 convolution layers. It's on Pytorch 1.5. It's to combine these models in the Gadgetron. Remember, in the generic chain, we go through all the steps. Then we finally got a complex image array. Then I said in last talk, we can go through the image reconstruction steps, which I added a real-time long-axis Cine AI analysis sketch for this concept. So what this sketch is doing is it's taking in a SMRT image array, calling AI models, detect the landmarks, then spit out another image array with landmark overlaid. So the key step is like this Python functions. You load landmarks, you load models, then apply models. We will go through this Python scripts for detail. But before we go to the other computer, here is what it's look like on the scanner. So we retro recount data sets. You can see this a 4-chamber view. Firstly, recount the image, then recount the image with landmarks for every face. You can play the movies. You can show in this AI that actually did a very good job. It's track the systolic and the diastolic pretty well. So here is here is something more we can do, just food for thought. With all these AI abilities, we can extend the imaging to do a lot more than it's traditionally doing. For example, in this case, we actually detect landmark, then we can compute longitudinal shortening as a biomarker. Then after you run a Cine scan, you can get all these biomarkers on the scanner as report, as showing here. So the basis of this kind of application, inline application can work is because deep learning now is really robust enough to make this can be clinically deployed. So let's switch to the other computer for a demo. So firstly, let's look at this this sketch we have. What it's doing is derived from this recon image base, which will receive an image array. It's insert after the scaling dash, which I mentioned in last talk. It's serving as an image analysis portion of the processing chain. So with this Gadgetron, you can design, the beauty of Gadgetron is actually now we can design the imaging acquisition, reconstruction, analysis as a whole application. It's really have no barrier to prevent us from optimizing this end-to-end. We don't need to treat them as separate steps. You don't need an external server which someone will have to mouse click it to get this job done. So in this sketch, you can specify what's the model files, which I had provided a pre-trained model files on the course website. Then if we go to this sketch, we will need to find and insert Python, Gadgetron Python path first. Then the case step is really just very small. You can load the model or apply model, or I also give another implementation. You can load and apply model in one call. So all this implementation is in this Python scripts. So it's similar like previous scripts. You first import the Pytorch modules. Then we have one function to load the model. So model was saved as the Pytorch script format. Then you can do this JIT loading. When we try to apply model, we can firstly detect whether we want to run this on CPU or GPU. Then for every image in the format of, this is a 2D series, so it's 3-dimension ROE1 N could be face or how many image we want. The key step is to you put your data into whatever device, either actually on CPU won't do anything, but on GPU it will convert data into GPU and put the model into GPU. Then we follow the formula, set the model in evaluation mode. We need to not let model to do the backprop. Then we can apply the model on the image. So because it's possible to apply this model on the GPU, I process whatever, how many image in batch, so it won't use all the memories. After this process, you can do a sort max, sort probability of landmark, then we can detect landmarks. So that's how this model doing. So let's see how this process is really working. I have a data set which in this folder. So I will delete what I got before. Then I will run this command. So one thing I often do is just call DOS in MATLAB to run this, so I can script everything. So we will run this command into this computer. Oh, sorry, I'm not in the correct folder. Okay, so data comes through, then it will firstly go through the generic recon chain, as you can see. Then if you're loading the model, now it's applying model, then it's detecting landmarks, then send everything over. I have a GPU on this computer. You can see it's using device is CUDA, then process every batch. It's running like 1.8 seconds. This is printed this model. You can see it's including lots of batch norm ReLU convolution layers. Then I have a few functions which we will load. The original series image is in series 1. The series with landmark overlay is on 100. So I will load them and plot them as a movie so we can see how this model performs. So on the left is a 2-chamber view real-time Cine series. On the right is AI outputs. So if we show them as a movie, you can see it's doing a very good job with one face with missing one. Okay, so that's how we can call some pre-trained AI models in Gadgetron. This example is on the course website, including this data sets. So that's come to the final remarks of this course, my session. What I want to say is this calling AI in Gadgetron actually give some new opportunities. I think the biggest opportunity is now we can treat the acquisition, recon analysis, even diagnosis as a whole workflow. We can try to optimize them end to end instead of separate them. When we're planning what kind of biomarker our clinical colleague needs, we can think, okay, maybe imaging protocol or sequence should be optimized in this way, then my AI model can work better. So we really not necessary to put them as unrelevant modules. We can think them as one whole package we can offer. And the Gadgetron infrastructure actually has designs and already rather powerful, I have to say, infrastructure to support all these steps. And I showed several examples we did along this way. So that's pretty much summarized my session for this. But I do have a little bit other remarks. So this year was 10 years of Gadgetron. So this project has been active development, as you're showing here, for 10 years. So many people contribute. So it's really growing. So we have this very innovative communities. It's truly lucky for us to have this community still growing. For us, actually, we as NIH, we keep pushing these projects, and we actually deployed Gadgetron on many hospitals. As you can see, the rather big network across the world. So Gadgetron is not only a research tool, but it can also be developed as a imaging tool, which can make the real world impact. So for that, thank all of you. This concludes my talk.
It was really a great talk, and it showed, yeah, so that we have a lot of opportunity and perspective using it. Maybe we can we can start the question, or is there any people in the audience that have specific question for Hui on this topic? I have some in case. I'm not really familiar, but I try to do a bit of machine learning. Usually, the model you use need a fixed image size. So, but in the protocol, in MRI, they are quite normalized, but sometimes depending on the body size, you need to adjust the fold for the patient. So are you rescaling the image each time before sending it to the model, or your model is using any size?
You can do both. So normally I upsample the image to a fixed resolution, for example, 1 millimeter squared, then fit to the model. It's also possible if your model has a full convolution architecture, it's maybe handle a variable image size. But it's also subject to the training. So if the training, including the data augmentation, is robust to the object size changes, then yes, you can input different size into the models. But most common way I'm doing is to firstly upsample the model, then give it a fixed size.
Okay, thanks. And I have, in case, a second question. It's more practical question related to the number of sites that are supporting the Gadgetron. So in practice, you're sending, I guess, some Docker image to each hospital, and in place you have people that can put the image on the scanner. This is how you organize such big things. It doesn't seem easy to do.
So some sites, they have people who can do this job. Then you just contact those people. Some sites, they don't receive updates so often. So maybe every year even. We have a few sites we work very closely. Then we have agreement that we can share some Linux servers, maybe even on the cloud. In those places, you can update them yourself. So it depends on, the situation. Another use case is to run the Gadgetron as a change root image on the scanner. So in that case, we can have the latest Docker that make the change root, then send the sites this installation package, then they can update themselves.
Okay, thanks.